Ordinary neutron stars. Ordinary neutron stars are the baseline collapsed stellar cores that don't pulse or emit strongly detectable radiation. These objects pack about 1.4 times the Sun's mass into a sphere just 20 kilometers across, making them so dense that a single teaspoon of neutron star material would weigh roughly 1 billion tons on Earth. Their surface gravity is approximately 2 billion times stronger than Earth's, meaning the escape velocity reaches around 100,000 kilometers per second. When newly formed, they maintain temperatures near 600,000 degrees Celsius, though they cool gradually over millions of years. While they do spin, their rotation isn't fast enough to create the lighthouse effect seen in pulsars. This makes ordinary neutron stars incredibly difficult to detect, since they're essentially silent and dark, emitting only faint thermal radiation that requires sensitive instruments to observe from across interstellar distances. Radio pulsars. Radio pulsars are the lighthouses of space, discovered in 1967 by astronomer Jocelyn Bell Burnell, who initially thought the signals might be from aliens. These neutron stars spin between 1 and 10 times per second, with their magnetic poles misaligned from their rotation axis, creating beams of radio waves that sweep across Earth like a cosmic lighthouse. Over 3,000 radio pulsars have been cataloged, and they're among the most precise natural clocks in the universe, with some displaying timing accuracy that rivals or exceeds atomic clocks. The regularity of their pulses is so consistent that astronomers use them for navigation and testing fundamental physics. However, pulsars aren't eternal machines. They gradually slow down over time as rotational energy gets converted into radiation and particles streaming away from their magnetic poles, eventually becoming too faint to detect with current technology. Millisecond pulsars. Millisecond pulsars are the speed demons of neutron stars, spinning with rotation periods between 1 and 10 milliseconds. The current record holder, PSRJ 174-8-2446AD, rotates an astonishing 716 times per second, meaning its equator moves at roughly 20% the speed of light. These stars achieve such incredible rotation rates through a recycling process, where a companion star dumps material onto the neutron star's surface, spinning it up like a cosmic merry-go-round. The extreme centrifugal forces at these speeds are so powerful that any mountains on the surface can't exceed a few millimeters in height before being torn down. First discovered in 1982 with PSRB 1937+21. Spinning at 642 rotations per second, millisecond pulsars are now used as part of pulsar timing arrays that hunt for gravitational waves rippling through the galaxy. Magnetars. Magnetars possess the strongest magnetic fields in the known universe, roughly 1,000 trillion times more powerful than Earth's magnetic field. These fields reach intensities around 100 billion Tesla, strong enough to warp atoms into elongated pencil-like shapes and theoretically rip the iron from your blood if you got within 1,000 kilometers. The magnetic field stress is so intense that the neutron star's crust occasionally cracks in violent starquakes, releasing bursts of energy that briefly outshine the entire sun. Only about 30 magnetars have been confirmed in our Milky Way galaxy, making them extremely rare among neutron stars. When their crusts fracture, they can produce flares visible across thousands of light years, with some outbursts releasing more energy in a fraction of a second than our sun produces in an entire year. Soft gamma repeaters. Soft gamma repeaters are a subset of magnetars that emit repeated bursts of soft gamma rays from violent starquakes as magnetic field stress cracks their crusts. The most famous example, SGR 1806-20, produced a megaflare on December 27, 2004, that released approximately 10 to the power of 46 joules in just 0.2 seconds. This burst was so powerful, it affected Earth's ionosphere from a distance of 50,000 light-years away, temporarily disrupting satellite communications and radio signals. Individual bursts typically last around 1/10 of a second, yet can release more energy than the Sun produces in 100,000 years of normal fusion. Only about 10 to 20 soft gamma repeaters are currently known, and they represent magnetars in their most active and violent phase before eventually quieting down over thousands of years. Anomalous X-ray pulsars. Anomalous X-ray pulsars represent another magnetar variant that emits roughly 1,000 times more X-ray energy than their rotational energy budget should allow. Unlike typical X-ray pulsars that get powered by accreting material from companion stars, these objects produce X-rays through the gradual decay of their ultra-strong magnetic fields, requiring no external fuel source. They rotate relatively slowly, with periods between 5 and 12 seconds, much longer than ordinary pulsars. About 10 anomalous X-ray pulsars have been confirmed, and they occasionally exhibit magnetar-like outbursts, which helped astronomers realize they're actually magnetars, rather than a completely separate category. Their steady X-ray luminosity reaches around 10 to the power of 35 ergs per second, powered entirely by internal magnetic field evolution, rather than rotation or accretion. X-ray pulsars. X-ray pulsars are neutron stars locked in binary systems where they gravitationally pull gas from a companion star, creating spectacular high-energy light shows. The stolen material spirals inward through an accretion disk, where friction heats it to temperatures exceeding 10 million Kelvin, hot enough to glow brilliantly in X-rays. The neutron star's powerful magnetic field funnels this superheated gas toward its magnetic poles, creating intensely bright X-ray hotspots. As the star rotates, these hotspots sweep in and out of view like cosmic searchlights, producing the characteristic pulsing X-ray signal. The accretion rates can reach between 10 to the power of 16 and 10 to the power of 18 grams per second, and orbital periods range from hours to years, depending on how far the companion star orbits from the neutron star. Gamma-ray pulsars. Gamma-ray pulsars emit the highest energy light in the electromagnetic spectrum, producing photons with energies millions of times greater than visible light. These neutron stars accelerate particles to nearly the speed of light within their intense magnetospheres, generating gamma rays with energies ranging from 100 million to 100 billion electron volts. The Fermi Gamma Ray Space Telescope has cataloged over 200 gamma-ray pulsars since its launch in 2008, revealing that some pulsars emit most of their energy as gamma rays rather than radio waves. The famous Vela pulsar, which spins 11 times per second, actually radiates the majority of its power output in the gamma-ray spectrum. Interestingly, some gamma-ray pulsars remain completely invisible in radio wavelengths, only revealing themselves through their high energy emission, fundamentally changing how astronomers search for these objects. Rotating radio transients. Rotating radio transients emit sporadic radio bursts instead of the steady pulses characteristic of regular pulsars, fundamentally challenging our understanding of neutron star emission. Discovered in 2006 while analyzing archival data, these objects produce brief 2 to 30 millisecond radio bursts separated by intervals ranging from minutes to several hours. Unlike normal pulsars that pulse reliably with every rotation, rotating radio transients only emit detectable signals during roughly 1 in 100 to 1 in 10,000 rotations, spending most of their time silent. Scientists believe they might represent dying pulsars whose emission mechanism is failing, or perhaps display extreme nulling behavior, where the beam simply switches off for extended periods. Approximately 100 rotating radio transients have been identified, and their sporadic nature means many more likely remain undiscovered in our galaxy. Black Widow pulsars. Black Widow pulsars are millisecond pulsars systematically destroying their companion stars through intense radiation and particle winds, named after spiders that devour their mates. These aggressive neutron stars blast their companions with such powerful radiation that the companion star's mass gets stripped away at rates around 1/10 millionth of a solar mass per year. The companion typically gets reduced to less than 1/10 the Sun's mass and will eventually be consumed entirely, leaving the pulsar alone again. The pulsar essentially recycles itself by first spinning up from accreting the companion's material, then destroying what remains of its benefactor. PSRJ 1311-3430 represents an extreme example, where the companion has been whittled down to just 0.01 solar masses, barely more than a large planet, and orbital periods for these systems typically range from 1 to 9 hours. Redback pulsars. Redback pulsars are similar to black widows, but their companion stars retain more significant mass, typically between 0.1 and 0.4 solar masses. Named after Australian redback spiders, these systems represent an earlier evolutionary stage where the companion is being evaporated more slowly, giving astronomers a chance to study the process in action. The dense material streaming from the companion periodically blocks or eclipses the pulsar's signal, providing valuable information about the mass transfer rate and orbital dynamics. Some redback systems, like PSRJ 1023 plus 0038, display fascinating transitional behavior, switching between states of low and high accretion activity over periods of years. Orbital periods typically range from 2 to 9 hours, and these systems serve as crucial laboratories for understanding how millisecond pulsars form and how binary star evolution proceeds under extreme conditions. Central compact objects. Central compact objects are mysterious young neutron stars found at the centers of supernova remnants, less than 10,000 years old, yet they show no pulsations or strong magnetic activity. These objects emit only weak thermal X-rays without any detectable radio pulses, gamma-ray emission, or magnetar-like outbursts that characterize other young neutron stars. Their magnetic fields measure around 10 billion Gauss, extremely weak compared to typical young pulsars, which can exceed 1 trillion Gauss. Scientists believe they may have been born spinning very slowly, or perhaps their magnetic fields are somehow buried beneath the surface. Only about 7 to 10 central compact objects have been confirmed, with the famous example residing at the heart of Cassiopeia, maintaining surface temperatures around 2 million Kelvin. These quiet survivors challenge standard neutron star formation models and remain among the least understood compact objects. X-ray dim, isolated neutron stars. The Magnificent Seven are a special group of 7 nearby isolated neutron stars discovered in the 1990s that are abnormally faint and cool compared to typical neutron stars. All 7 reside within approximately 1,500 light-years of Earth and have ages between 100,000 and 1 million years, making them middle-aged by neutron star standards. Their surface temperatures measure only 50 to 100 electron volts, extraordinarily cool for neutron stars, and they emit purely thermal X-rays without any non-thermal radiation components. Rotation periods range from 3 to 11 seconds, and they're slowing down predictably over time. The closest member, RxJ 185.6.5-3754, lies just 400 light-years away. These 7 objects appear to represent a distinct population of neutron stars with unique properties, though why only 7 have been found, and what makes them special remains an active area of research. Double neutron star binaries. Double neutron star binaries consist of 2 neutron stars orbiting each other, providing the ultimate laboratories for testing Einstein's general relativity under extreme conditions. The Hulse-Taylor binary, discovered in 1974, provided the first indirect evidence for gravitational waves by showing orbital decay matching relativity predictions exactly, earning a Nobel Prize. Some systems like PSRJ 0737-3039 are double pulsars, where both neutron stars emit detectable pulses, offering unprecedented precision for studying gravitational physics. These binaries will eventually spiral together and merge after millions of years, producing catastrophic gravitational wave events like those detected by LIGO observatories. When neutron stars collide, they create colonovae explosions that forge heavy elements including gold and platinum, seeding the universe with materials impossible to create in normal stellar fusion. PSRJ 0737-3039 will merge in approximately 85 million years. Quark stars. Quark stars are theoretical objects where the core pressure inside a neutron star becomes so extreme that neutrons themselves break down into their constituent quarks, creating a soup of free up, down, and strange quarks. According to quantum chromodynamics, this phase transition might occur at densities exceeding 10 to the power of 18 kilograms per cubic meter, potentially creating a quark matter core surrounded by a normal neutron star crust. These hypothetical objects would be smaller and denser than ordinary neutron stars, with radii around 8 to 10 kilometers instead of the typical 12 kilometers. RxJ 185-6.5-3754 has been proposed as a possible quark star candidate because observations suggest it might be too small for standard neutron star models, though this remains controversial. No quark stars have been definitively confirmed, and distinguishing them from normal neutron stars requires extremely precise radius measurements that push current observational capabilities. Strange stars. Strange stars represent an even more exotic hypothetical possibility, where the entire star consists of strange quark matter rather than just the core. According to the strange matter hypothesis, configurations of up, down, and strange quarks might actually be more stable than normal atomic matter under certain conditions, meaning a neutron star could completely convert into this exotic state. These objects would have crusts only millimeters thick or potentially none at all, with quarks exposed directly to space as bare strange stars. Theoretical models predict masses between 0.1 and 2 solar masses with radii of 6 to 10 kilometers. If the strange matter hypothesis is correct, these objects could theoretically convert normal matter they contact into strange matter through a runaway catalytic process. Strange stars would help explain some observations of ultra-dense compact objects, though they remain purely speculative, with no confirmed detections, and many physicists doubt whether strange matter is truly absolutely stable. If you want to see more insane cosmic objects explained, click the video on screen now.